Hi and welcome to a lesson of multivariable calculus. So in the previous class, we started introducing multivariable functions, and we talk about domains, range of multivariable functions, right? Now we are going to talk about space, three-dimensional space, right? So all we are going to do in this course is dealing with three-dimensional objects and three-dimensional functions and higher dimensional functions as well, right? So now let us talk about two-dimensional plane first. So if this is x-axis and this is y-axis, then we know that uh, if we say an equation x equals to 3, to represent this equation on this Cartesian plane, what we do is we fix point at x because it's x equals to 3. So x equals to 3 is fixed, and then a line is extended in the y direction parallel to y-axis. So this is the equation of x equals to 3. Similarly, if I say y equals to 5, then what we do is we fix a point at y equals to 5, and then we extend the line parallel to x-axis. So this will be the equation of uh, line y equals to 5, right? Now, what happens in three-dimensional space is that if we need to sketch this equation x equals to 3, then we know that in three-dimensional Cartesian system, we have x, y, and z dimensions. Therefore, now what happens here is these are three axes, x, y, and z. Now, if I want to draw x equals to 3, it means that I have to fix a point at this x equals 3. And then now, on this point, we have to extend in x direction as well, y direction as well, and z direction, right? So we have to extend this in both the directions because we have two other axes now. So it will be like this. It will look like this. So it will be a plane actually, right? So it will be a plane like this. It will be a plane like this. And the center, let's say it will be on the, okay, let me draw it again like this. This is x-axis, this is y-axis. You can see here this one, it's drawn already, that this is z-axis, this is x-axis, and this is y-axis. And we fixed a point at uh, x equals 3, and then we have to extend this in the y direction and in the z direction now. So this will be a plane now, right? So this will be equation of a plane. So this is a plane. So in 3 dimension, we have x equals to 3 as a plane, unlike in the 2 dimension where we have x equals to 3 as a line, because we have one more dimension there in 2 dimensional Cartesian system. Therefore, we can only extend in one direction. So here we have two more directions other than x. Therefore, we are going to extend this in two more directions, and we are going to get a plane like this. So this is a plane, right? This is a plane. And similarly, if we want to draw z equals 4, then what we are going to do is we are going to fix a point at z equals to 4 and then extend it in the x and y directions, right? So this will be extended in the x and y directions, and therefore we are going to get a plane again. So it's infinitely extended in both directions, so we have a plane like this that is parallel. This plane is parallel to xy plane, right? So this is parallel to xy plane, and here this one is parallel to yz plane, this thing here. So this is how we can sketch these surfaces represented by the equations of this kind, right? Now let's move on to equations of lines and planes in space. So in two dimension, again we can start with two dimension. In two dimension we have x and y axis. So the representation of a straight line in this two-dimensional space is that y equals to mx plus c. So this is a slope point form, slope intercept form of equation of line, and we have multiple forms. We have slope intercept form, we have 2-point form, we have two intercept form, and slope normal form, and different forms, right? Now in this case, in the case of 3D, what we do is we write the equation of line in parametric form. So we have parametric representation, and also we have a symmetric equation of line. So in general, these two representations are used in three-dimensional space, right? And what we need for the representation of a line is that we need a parallel vector. So if we have a line, here we have a line, this is a line in 3D, this is a straight line. So to define its equation in parametric form, what we need is we need a parallel vector. We need a parallel vector that is known to this line, parallel vector to this line, and a point on the line, right? So any point on the line. So we have infinite many points. Let's call it P naught. So if we knew that what is P naught, and then choosing an arbitrary point on the line, we can just define its parametric uh, expression for this line if these two things are given, right? A parallel vector and a point lying on the line. So now we know that if one vector or one line is parallel to other line, then what we can do is we can just represent one vector in terms of the other vector with some scalar multiple, right? So if this is vector v, let's say, having coordinates a, b, and c, and these are the points. Again, if I join these two, so I can find a position vector, because if I call it the initial point, so this p naught is the initial point, and we have also the terminal point, that is p. Then from these 2 points I can just find the position vector, that is p, p naught p, right? That is p naught p. So if I have this p naught p, and I have a vector v, this one, then I can just represent this p naught p in terms of this vector v with some scalar multiple. So t here is a scalar multiple, which we will call parameter because these are parallel, right? So we can express in this form. So first of all, what will be p naught p? So p naught is nothing but it is x naught, y naught, and z naught, and p is simply x, y, z. So if I want to find p naught p, then we have p minus p naught, right? So we have to subtract the corresponding coordinates. So z minus z naught, right? So just finding the positions. So this is p naught p, and what will be tv is t times a, b, and c. Now we already said that these two things are equal, therefore we can equate these two and compare corresponding coordinates. So if I compare the corresponding coordinates, so this is x minus x naught, it will be compared with at, y minus y naught compared with bt, and z minus z naught compared with ct. So we will get the parametric representation of a line, right? Equals bt, and z minus z naught equals ct. So this is a parametric representation of a line. Now let's see an example to be more clear. So now see this example. So they have asked to find the parametric equation for the line passing through the point and parallel to the vector v, right? So a point is given. We have a line, this blue line. So this line is given and a point is given on this line. A point is given, P naught on this line, and a parallel vector is also given. So a parallel vector, this vector is given. The coordinates of this vector are given. So these are parallel, therefore we already have an expression for this relation that P naught P equals TV, right? So if I choose P arbitrarily here at some point, this P, X, Y, Z, it's an arbitrary point. Now this P naught P is simply X minus X naught, Y minus Y naught, and Z minus Z naught. So X naught, Y naught, Z naught already given, that is P naught. And also the vector V is given, that is 1, 2, and -2. So we have the parametric representation X minus X naught, that is -2 equals to AT. So here we have A equals 1, B equals 2, C equals -2 from this vector V that is parallel to the line. So we will have this equals T, so we get X plus 2 equals T. And then for Y, we have Y minus Y naught. So Y minus 1 equals to BT. So B we have 2. So it will be 2T. This is for Y. And for Z, Z minus Z naught, that is 3 equals CT. So it's -2. So that is for the Z, right? So we have this parametric representation for the given line. And we can also write it this way, that if I write from here, that T is equals to X minus X naught over A. Again, T is equals to Y minus Y naught over B, and T is equals to Z minus Z naught over C. So if these all are equal to T, therefore these all will be equal, right? Because every component is equals to T. It means that these all components are equal. So I can write in this way. I can write in this way that X minus X naught over A equals Y minus Y naught over B equals Z minus Z naught over C. So this is also the representation of the line, and this is called symmetric equation. Symmetric equation of the line. Okay, so now we have two representations. One is parametric and second is symmetric, right? So it depends on the question that what we need to find. Now for in this case, in this example, they have asked that find the parametric and symmetric equations. So we need to find both for the line L passing through the points P and Q. Okay, now we are given 2 points. So here we don't have the parallel vector, but we are given with 2 points so that we can find a parallel vector. So let's say that we have this coordinate system X, Y, Z. So first point is -3, 3, and -2, right? So it's in negative X, positive Y, and negative Z axis. So let's consider that this point is somewhere here in negative Z axis, negative X, and positive Y, somewhere here, like this vector, for example, going down, going inwards to the screen, right, and downwards. And the next point, that is 2, -1, 4. So 2, -1, 4 is in the positive X, negative Y, and positive Z direction. So negative Y direction is here. This is negative Y axis. This is positive X, and this is positive Z. So it's here, right? Somewhere here. So let's say this point is here. Okay, so this vector. So like this. So we have two vectors, P and Q. Okay, Now what we can do is we can and these two are on the line, right? So I roughly draw these two vectors, so it just does not look like a straight line, but it will be a straight line like this because 2 points are lying on this line. So let's say P is here and Q is here, right? So maybe it look like this, something like this, that is extending from sorry, need to remove this, and this is z axis. So let's say this line look like this. Okay, so this is point Q and this is point P. All right, now we need to find a parallel vector. So what we need, what can we do here is that if I find PQ, so PQ is nothing but it's Q minus P, and this will give a vector that is on the given line, right? So this will give a vector in the direction of P like this. So it will be on the given line. So therefore it is collinear to this line. Therefore it's also parallel to this line. And so this is how we can get a parallel vector, by just finding position vector of these 2 points by considering one of the point as a terminal point, another point as one of the point as the initial point, that is Q, say in this question, and P as a terminal point. So now Q minus P is simply 2 minus minus 3, 2 minus minus 3, so it's 5. Then minus 1 minus 3, it's negative 4. Then 4 minus minus 2, so it's 6. So this is the vector PQ, that is the parallel vector to this line. Okay, so the parallel vector is here, and since 2 points are given and both are on the line, so whatever point you want to choose, you can choose, and uh, just take it with this vector V, that is parallel vector to the line. And by using the parametric representation that we already did in the previous question, that we say that x minus x naught equals AT, y minus y naught equals BT, and z minus z naught equals CT. So let's consider P as the point. So P is 3, negative 3, 3, negative 2. We can also choose Q. It's up to you, whatever point you want to choose, because both the points are on the line, right? And the vector V we get, it was 5, negative 4, and 6 by just finding the position vector of these 2 points, right? So it will be x plus 3 equals 5t, y minus 3 equals negative 4t, and z minus minus 2 to plus 2 equals 6t. So this is the parametric representation of the given line. Now we need to find the symmetric equation as well. So just what we need to do is we have the symmetric representation as x minus x naught over at. Sorry, a, not at. It's only a. It's a, not at. So we have x minus x naught equals a, y minus y naught over b, sorry, z minus z naught over c. So we have all these points, so it will be x plus 3 over a, that is 5, equals y minus 3 over b, that is negative 4, and z minus z naught, so it will be plus 2 divided by c, right? So this is the symmetric equation for the given line. Okay, so this is how we can just simply find the equations for the straight line in the x, y, and z Cartesian system. Okay, now the second point of this question is that at what point does L intersect the xy plane? Now this is very easy. Now what happens here is that we already said that these 2 points that are given here, they represent this point P is in the negative X, positive Y, and negative Z direction, right? In this octant. And this is in the positive X, negative Y, and positive Z octant. So the line will obviously cut the XY plane. Why? Because if I have the axis like this is X, this is Y, this is Z, therefore the line, now this is negative Z, again this is negative X, so sorry, this is negative Y, not negative Z, this is negative Z, right? This is negative Z. Now this point here that is in the negative X, positive Y, and negative Z direction, it means it's somewhere here that is inside, that is somewhere here. We can say that this from starting, if I start from here and draw a vector, so it will be go downwards and into the screen, right? So this point here, and the other point is somewhere here, positive X, so it will be coming out of the screen. All right, so coming out of the screen, but in the left direction. So positive X, positive Z, but negative Y. Now if I join these two lines, so the line starts from here and cuts the XY plane, because now it's going down, right? So this part here, this whole part here, this part is XY plane, right? So for going inwards, this line will cut and then cut XY plane and then touch the point that is below the XY plane, right? So since this is negative X, this is negative Y, and this is negative Z, this straight, it will be straight, right? And so now we need to find the point of intersection. So if it intersects the XY plane, so at the point of intersection, since it's cutting XY plane, therefore the Z coordinate, it will be 0. This is clear, right? Because it's cutting the XY plane. So Z is 0 at XY plane. Now by exploiting this condition, we can just find the point of intersection, right? So since Z equals 0, therefore we can, at this point, right, Z equals to 0 means we can use this equation to find T. Okay, so Z naught is -3. So negative times -3, where Z is 0, equals C. What was C? We can just look at it. So C is this A, B, C. This is 6, right? 6. So C is 6. Therefore, it will be 6T, right? Or I have done some mistake here, I think. Let us correct that. So we have Z equals 0. So the third parametric equation we have, that is Z minus okay, so it's +2. Okay. So Z plus 2 over 6 it will be, not 3. So it will be Z plus 2, because we have chosen P, point P, that was -3, 3 and -2. So Z naught means this is -2, so Z minus 2 equals CT, and C is 6T, right? So Z is 0 at the intersection, so we will get 2 equals 6T. Therefore, we get T equals 1/3. Now we can put this T is equals to 1/3 in the equations of X and Y equals BT. These two equations to find this X and this Y, because these are already known, right? So we will get x as -4/3 and y as 5/3. We just need to put this point t equals to 3 in these two equations. I will show you here these two equations, this one and this one. So x equals -3 plus 5 times 1/3. We will get -4/3, and uh, y equals 3 minus 4t, so 3 minus 4 into 5/3. So this will be okay, let's check. Okay, it's sorry, 1/3. It's not 5/3. It's 1/3. T is 1/3. So this is equals to 9 minus 4, that is 5/3. So these are the points. So x is 4/3, y is 5/3, and z is 0 at point of intersection with xy plane. Okay, so this is how we find the point of intersection of the line with the plane. Now, example 3 is also associated with this content, this topic. So we are given two lines now. We are given the equation of lines, parametric equation of two lines, and we need to show that these lines are not parallel to each other. And also they ask that do lines L1, L2 intersect? If so, find the point of intersection. So we need to find the point of intersection if they intersect. And the first one asks that first thing we need to see is that either these are parallel or not, right? So it's obvious that if these two are parallel, then they are not going to intersect. But in 3D, it is not necessary that if two lines are not parallel, so that they will intersect. It is not necessary. They might not intersect. So two lines can be parallel and not intersecting in the three-dimensional system. But in two-dimensional system, we know that if two lines are not parallel, then obviously they are going to intersect. But it's not the case in 3D, right? Because one line can be in XY plane, other lines can be in the YZ plane, and they may not be parallel, and then they will not intersect because both the lines are in different planes. So now we need to check here what's happening. Now we are given x equals 1 plus 2t for the first line, L1. Let's say it's T1, and 2 minus 3 T1, z equals 2 plus T1. So for L2, we have 3 minus 4 T2. Okay, x equals, so representing it with T2 because this is a different line, and y equals 1 plus 4 T2, and z equals -3 plus 4t. Now, if you remember these parametric equations and what they represent, what these represents, this one, this two, and these two, -3 and 1. So if two lines are parallel, now see here that if two lines are parallel, then the vectors that they're parallel vectors that we talk about, that we need a parallel vector to find the parametric representation of a line, will also be parallel, right? If this line is parallel to this vector and this line is parallel to this vector, and we have found the equation of line using these, then these two vectors should be parallel. So the parallel vectors, we can find the parallel vector for this line. It will be this 2, -3 and 1. 2, -3 and 1, because these are A, B, and C, right? Because we have x equals x naught plus at, y equals to y naught plus bt, z equals to z naught plus ct. So these are A, B, C for line 1, and here we have -4, +4, and 4. So let's call it v1, let's call it v2. So we have -4, positive 4 and 4. So these are ABCs of the second line. Now we can see that these two vectors are not parallel because none of the vector can be represented in form of the other vector, right? Because none of the vector is the scalar multiple of the other vector. For instance, we cannot write v1 equals to some scalar times v2. We can never write because the coordinates are not in the way that we can write, right? So these lines are not parallel. So their vectors are not parallel implies that the lines are not parallel. So this is established that the lines are not parallel, right? Lines are not parallel. Now, what next is we need to find that do these lines intersect, right? Now, if these lines intersect, it means that the lines should have some common point. For instance, if these two lines are intersecting, then this point is a common point. So this point is common for both the lines. Therefore, x, y, and z at this point will be same for both the lines. Therefore, it means that we can say that at the point of intersection this x and this x is equal. So I can write 1 plus 2t1 is equals to 3 minus 4t2. So I can arrange this. I will get 2t1 plus 4t2 equals 2, call it equation 1. And then again this y should be equals to this y. Therefore we can write 2 minus 3t1 equals to 1 plus 4t2. Now arranging this, I will get 3t1 plus 4t2 equals 1. This is equation 2. Now I can solve these two equations in two variables. So I can solve it simultaneously to get t1 and t2. So after getting t1 and t2, what I can do is I can just put this t1 here for z and t2 here for z, right? So z equals 2 plus t1 and z equals negative 3 plus 4t2. Now if these two are equal, the values that I get here, if these are equal, then I can say that the lines are parallel. Sorry, lines are intersecting, right? If these two are equal, because now we have the common points x, y, and z, right? But if these two are not equal, then we can say that these lines are not parallel, right? So this is how you can show. So by finding t1 and t2, just plug t1 and t2 in the z equation of z and check whether these are equal or not. If both z's are equal for t1 and t2, then we can say that the lines intersect. If not equal, then we will say that the lines do not intersect, right? So this is an example 4, flight path of two airplanes. You can solve it by yourself. Line 1 and line 2 are given, and we have to see that whether these are intersecting or not. So in the next class, we are going to start equations of planes in space. So thanks for today, and thanks for watching the lesson.